Okay, so last lecture we went very slowly and we started to speak about neural networks. So like now, some people in machine learning say that okay, statistical learning theory it's all about bias variance trade-off, and the fewer parameters, the better generalization. So try to use as little as possible. But this is, and then they point out nowadays in neural networks is opposite philosophy. The more parameters, the better you will perform. So they say all of this statistical learning theory is nonsense. But this is kind of like old view and or superficial view in statistical learning theory. So we will address this. Although neural nets, it's now only in the beginning that people start to understand a few things, and still very little is known. But we will explain why increasing the number of parameters doesn't lead to overfitting in neural nets. And we started, the basic idea is that over-parameterized neural nets, they have many solutions, and gradient descent will pick a random solution from it. And it turns out that the random solution has good generalization properties. And so we will see that that when we train, we fix in a certain sense one level to think about this is that when we fix a solution, then there is a certain randomness in the solution that's already present from the beginning, and the extra information that is added is somehow, in some sense, of a small dimension. And we can just make this very precise. So let us remember what is gradient descent. So we will start with a vector that's 0, and this one, this is just so we have a neural network, and it's described by a function. So it receives two parameters, W and X. And so W lives in a high dimensional space, M. M is very large number. X is the input dimension, which is some number D in our course. The input dimension doesn't matter. So I will just delete this. And we have a training set, X1, Y1. I will speak as usual about regression. And the number of training points is N. It's a little bit annoying because M is parameters. I mean, for speaking, it's annoying. For writing, it's no problem. And so they live in X times R. We will speak about regression. Then I will use the vector f of W. It is the vector that contains all the values for W on the training points. So f x n W. And I will use the vector y, which is just all the labels. Yn. Okay.
F is a linear function, yes?
Yeah, f is the function that evaluates the network.
It's a linear. Because you said regression.
No, with regression, I don't speak about linear regression. Regression just means that the values yi are in R. So I do the general case classification, a special case where by coincidence all values y are equal to 1. But it will be a bit strict. I mean, there is no reason to restrict, so I will do it more general. Yeah. And so in gradient descent, so F evaluates the network. We've seen it many times. So we use the input X and the weights of, it's better to flip the arguments like I did here. X1. But it's not so important. I mean, it's clear. I will always use W for weights. Okay. And so gradient descent starts by W, and it will take each item. So each variable will be taken from independent Gaussian. So there is some randomness. We pick W randomly. It's kind of standard practice to do it like this, but how it does is not so important at the moment. And then we generate a new team. We update the weights and we will use a very simple update mechanism. We will use a constant step size, and then we will subtract the gradient of the loss. Loss will be let me think. I forgot a little bit. We will speak about now. We will speak. Okay, I didn't prepare very well. So very important question. So for now, loss will be. I just have to check whether it's general or a quadratic loss. Oh, I don't need loss at all. But okay, then we can. And I don't even need gradient descent, except, okay, I need no loss at all. So that's why I couldn't remember the properties. No, it's just that excuse in my hand. Okay, so for now, it doesn't matter which loss we, no. No, we need quadratic loss. Okay, so the loss here will be W will be equal to norm of F of W minus 1. Oh, I'm the two norms. All norms for vectors will be two norms. Okay. Now let's and I forgot one now. I will update the notes tomorrow. I also forgot the R1/2 in several places. Okay, and this, so let us now compute this gradient. We did it yesterday in the seminar. So gradient with quadratic loss. So we will iterate over all the points and look at the gradient in all the points. And then we have this notation where I say that this is equal to W of F. Let me write it here. W of F is equal to, oh, sorry for all the notation. Ij is equal to delta Fi dWg.
What do you mean by Fi?
So F is a vector here, the ith component. So when you put xi in the input. So we have in the rows, we have the different derivatives. And in the columns, different points. So when we look to the loss here, then we want to have a gradient. So
But our gradient should be right.
yes, it should be a standing vector, but so we will transpose this thing and then multiply by Fw minus 1. So when we need to have a sum over all inputs. So that's why we have a standing vector. We will sum over all inputs, but the different derivatives become now. So when we change the column, when we change the row, we change the derivative, and that's what we need for the gradient. So this is the right expression. Okay. So now we understand a little bit what is gradient descent and what is the remarkable property. If the neural net is very wide compared to its depth, it turns out that this matrix doesn't change during training. So basically it means that second derivatives are close to 0. So this matrix doesn't change during training. And that means that when we generate a random W is 0, so two conditions, net is wide compared to depth, and W0 is taken randomly. For specific W0, anything is possible. And And okay, third condition is that the definition of our function f needs to have certain normalization that's in a reasonable sense. Okay, so under these conditions, this matrix remains stable, and I will explain why. But let us first think about the consequences. Let us pretend that this matrix remains constant. So then what happens is that this gradient, it will take column space of transpose, so a linear combination of column space of the transpose. So that means that at any moment, WT will be an element of W0 plus the span of the gradients of L. Gradients of L, again, are linear combinations of these, the columns of this transpose matrix. The transpose matrix are the gradients in the different points. So we have here in the span of gradient of F, so the W gradient, W of x1 till gradient, the W gradient F, W of x. So we fix second argument to be one of the elements of the training set, and we take the gradients to the W's. Okay, so this is kind of remarkable property. So what does it say? So here we have so W lives in Rm, which is huge dimensional space. But the solution after fixing W0, the solution is taken from low dimensional affine subspace. So the dimension is n. And this is equal to n, and this is much smaller than n. And so this is a part of the explanation why neural nets do not overfit. So there is empirical observation. At least 3 years ago, many all papers, it's not so clear what happened. Many papers say that if gradient descent converges fast, it generalizes well. There are some people who try to experimentally validate this. I also tried to check it, but it was very small effect. I could only find, and now doesn't look like people speak a lot about this. But okay, there seems to be at least a little bit of effect, and this can actually be nicely explained with this theory, with the stability of the gradient, and moreover the stability of the neural tangent kernel, which I will speak about later. But now, before doing these advanced things, I will prove that these matrices, they remain stable. So let us look why when we change W, when we update W, why do they change? Why do they stay? Why does the gradient stay constant? And so we will focus on the neural net with one layer. And that's what we started to do yesterday in the seminar. By the way, there is a major mistake in the seminar because I computed Hessian for neural net with ReLU activation, but then any conclusion does not hold because ReLU doesn't have continuous second derivative. So it holds for any activation function except ReLU. So the small. Okay, but let me briefly repeat what we said in the seminar. So first, let us have about for the gradient. So the update. So let us take a gradient in 2 points. So okay, let us fix x. And I will drop the argument x. And then I will say that gradient in W, I will bound it by W prime. I will say that this is bounded by the distance between the W's times the maximum of the two norm of the Hessian. So okay, let me write it better. So this is a small lemma, and we spoke about it yesterday. W prime minus W times maximum W for some point W tilde inside W and W inside the line segment of W and W prime of the Hessian inside W tilde, and we take the two norm of Hessian. Okay. So Hessian we discussed. Do I need to repeat it? We discussed previous lecture in full detail. Just partial derivative. So
Yeah. The second derivative.
yeah. Okay. Yes. So how can this be proven? So
Because just I think some integral inequality.
yeah, exactly. So we will take integral and okay, this notation I think I don't need it for some time. We'll just start with let us look at GW minus GW. So let us take a fixed vector V and some real parameter T. So vector parameter, real number.
G is an arbitrary part.
Yeah. And so how can we express it's a vector function. So this can indeed be expressed by integral of gradient of the derivative of the G. So this is D of G and the value W plus T and V times dt, and we integrate T from 0 to 1. Okay. And this is that's it basically. So we can bound this derivative by its maximum. And so by the two norm. So here we have a vector that's bounded by the two norm dg of times v 0 to 1 v dt. So now we can draw the integral. Sorry, the v is not needed. So we can just draw the integral, but then
It's not like we should take the norm. So the norm of the integral is less or equal than integral of the norm.
yeah. That's what, yeah.
We didn't put norm.
Okay. Yeah, and then integral. Now let's look to this norm. So we will take the two norm of the matrix times the norm of V. So just I can drop the integral and then I apply. So remember, I didn't say what is two norm. So for a matrix M, the two norm is equal to the maximum of the norm of M times V, the spectral norm, M times V, for V being at most 1. Okay, so we so now we can normalize V, and we get this inequality almost by definition of two norm. Okay, and now we are finished. Oh, sorry, here I forgot to write the maximum. Maximum over T. Okay, so that will be the maximum. Okay, T going from 0 to 1. Again, this thing and then we are done.
Mhm.
So this is our proof. And so now you will see our plan. We will see that the change of the gradient is a product of two things. Each thing we will prove to be small. And we will start with the second thing, prove that Hessian is small. I will only do it true for all neural networks that are not 2D. So the ratio depth divided by width is reasonably small, but I will just do it for single layer network. And then I will modify the lemma we proved last time, or I mean, take a corollary from the lemma of last time to prove that this is bounded by a constant that does not depend on m. So I will basically prove that this goes down with 1 over square root m plus something logarithmic, maybe. And this is bounded by a constant independent of m. And so the conclusion is that if neural net is very wide, then the product will be bounded by a constant. Will be go to 0. Okay. So let us look at our network. So this whole theory I'm presenting, it is a bit difficult theory, but pieces are difficult. Some pieces are easy if you take Radu function, and other pieces are easy if you take any function except Radu function. So more precisely, this one we can prove to go to 0 for any function except Radu, and this one, okay, this one to do the full proof. You need in some steps, it really helps a lot to understand what's happening. Okay. But most steps is for helpful for any. Okay. And that's enough. So now let us just compute a Hessian for a neural net with one hidden layer. So, yeah, we did it last in the seminar, but I think it's interesting to go over it. So we will have linear output, and here we will have sigma activation. And we will assume that it's sigma smooth. It means the second derivative is bounded by a constant. So that's why ReLU is not good. And then we will have some certain small dimensional input here. We will fix the weight of the second layer just to speed up explanations. It's probably going to be homework to do the same computation with variable weights on the second layer. If I manage to invent enough homework by tomorrow, because we're close to the deadline. I will abuse notation a little bit. I will say that there are m neurons in the hidden layer. So the parameters is m times d, because I will fix the weights on the top layer and I fix them to be -1 and +1. So just any choice will help to prove that Hessian has bounded to norm. Okay, so now I should write down what is the output function. So f w so fx of w is equal to 1 over square root m, sum I smaller than m. So know that we have some normalization here, and it needs to be right to have reasonable calculations and to understand what's going on. And here we have sigma. Oh, sorry, let's put some structure on the variable string. So fx of w1 wm. So here these are wi are vectors that live in Rd. So, and this, here I write concatenation of vector into one long vector. So one till Wm is just one vector of length m times. Okay, and then we have some notation and we take the dot product with Wi, and that's the output of our network. So now we need to know the Hessian. So this is slightly annoying because Hessian, so we use two indices to specify one weight. And so we choose the neuron with first index and then the input to which should go with the second index. So Hessian has four indices. J prime of W. And so it is equal to, okay, I will save a bit of time. So first, when we go to different neurons, so the weight, if we change the weight on this neuron, it doesn't affect so we have linear output, right? So we add up the output here. So if we take the, okay, so so here we have a sum. That means if we take the derivative to a weight on the ith neuron, from the sum only one term remains. So that means that if I is different from I prime, we get 0. So the first thing that we will have for the Hessian is an indicator function that I should be equal to I prime. And then when we take derivative to Wi, the j component, then xj appears in the front and we take the derivative of sigma prime. So this chain rule. And so when we do it 2 times, we get x times Wi, xj, xj prime. So that's expression. I hope it's big enough. People disappear. So let me play safe. Yeah, I will just copy it. 1 over square root m. I equals I prime. So now the question is, why is the 2 norm bounded for this matrix? So know that I use pairs of indices. So in your mind, you need to flatten this. And what we see is that this is a block diagonal matrix. We have small blocks, it's almost diagonal matrix. So the first question, imagine that the definition D equals 1, then we have a diagonal matrix. Yeah, why can be bounded by something that does not depend on M? Is the first question. So while I write this, y, x, Wi, so change x, change. Okay. So D equals 1, H I prime is diagonal. And so when we multiply H by a vector V, then and we take, so then we see that all the components of V are multiplied by a vector, which is bounded by something that sorry, I mean by a bound that does not depend on M, I mean ignoring the square root. So a constant divided by square root M. So but we still have these W's here, which are okay, but there is sorry, I said here sigma activation and sigma double of E is bounded by a constant. I forgot to tell, and so now we can bound this by a constant. So H of V, if we multiply by V and H is diagonal, then each component of V is bounded by a constant. that is bounded by the upper bound of the diagonal element. So, well, we can say that the norm is smaller than the max of HI prime times norm of V. And this maximum goes down by 1, and so constant times 1 over square root m. So then we are done. Okay, now why is the general case also of this case? So constant will be a little bit bigger, but still independent of m. Well, actually, so here H is diagonal. So imagine that H is like permutation matrix, but not with ones, but any number. So it just H in every column there is at most one non-zero element. Then precisely the same reasoning holds. The norm of V increases by at most the maximum of an element in H, or absolute value of element in H. To be, well, they're all positive. Okay, I should say absolute value here. Of this.
And now we just multiply it by D.
Yeah, indeed. We just multiply by D because we can just view H as a sum of the matrices that are non-zero. So here the C will depend. Yeah, it's clear. Okay, so we understand why this is bounded. Why this goes down to 0 with 1 over square root m. Now, next task, let's prove that this is bounded for gradient descent. And so last lecture, we did already a part of the work. This was like this proof by, forgot again their names, Polyak Liasevich. Liasevich, yeah, Liasevich. So that's their result. And we need a little generalization or a corollary of this result. So we will show that okay. So what is the problem with neural nets is that this condition is we need to show that in each update step this gradient is large. But we cannot prove it globally for all values W of the neural net. So this is a property that holds around a random input, around the W0 in a small area, this property holds. And that creates some trouble of us. But thanks to a stronger corollary, we will also understand that if this holds, then the next update will be close to the previous point. So updates are small, provided this condition holds. Moreover, updates, the norm of the updates, so the norm of WT plus 1 minus WT, will go exponentially down, geometrically down. And so these two properties, like in the neighborhood of a random point, we are okay with this condition, and we stay inside the neighborhood, allows to recursively get a version where we get exponential convergence of gradient descent. Okay. Yeah, so by the way, and when I was young, when people train neural nets, they had to do it many times because they got stuck in bad local minima. So they even before calling the validation step, they saw that their error stopped going down and they restarted. So now people run it a few times and use a validation set to like get better precision on training set. So now it's the reason to do this has decreased a lot. Okay, so how do we get? Well, let us state the corollary. And corollary is quite technical because we need 4 parameters. And it is theorem, the theorem on page 8 of the lecture notes. For people on YouTube, there is a link below. You have a wiki page with the lecture notes there. I mean, let's be honest, 1 person in class, but then every movie gets like 50 watch hours after a year or something. So I should think. Actually, I should be more scared because if there were 50 people sitting here, I would be really nervous. Sounds kind of strange. No, 50 is maybe the only few movies. But okay, you never know in advance which movies suddenly people like to watch. Like once I screwed the lecture on hierarchy theorems for computational complexity, and that got 100 watch hours. No, not one. It got, I think, 300 view. I don't remember, but okay, it's one of the most watched movies. So. Yeah, and also I see like if I have a question and I ask to YouTube, the wrong explanations are more popular than the right ones because I tend to be a little bit more clever. And then in the comments, like, oh, they should kill all these teachers and the books because it's actually simple. And beta smooth. So beta smooth means 2 norm of Hessian is at most beta. Let's make more space otherwise. So you remember what is F? F has M inputs, N outputs. We pick the training set and they're the values of the endings. Okay, second assumption. We use quadratic loss. LW is 1/2 F of W minus Y squared. Satisfies this condition here. It's called UPL condition. So let me write 1/2 number of L of W T squared by L W T. And it does so inside a ball around a point W and 2C over mu at W0 minus 1. And here we have the 2 norm. So, and then the gradient descent with eta small enough. It needs to be smaller than C squared plus beta FW plus y minus y. And the 1 norm of this thing. And then satisfies the same conclusion here. So LWT smaller than 1 minus eta mu to power E LW0. That's our theorem. So let's prove this. So there are 4 parameters. C Lipschitz, beta smooth for the function f. So that means that C Lipschitz means if we change the parameters, then the values don't change too much. Our vector doesn't change too much. Beta smooth, it was so Hessian. So here we look, if we fix 1 point, for each point, the Hessian is at most beta. Beta. Okay. Then we have from the PL condition, we have constant mu. And then we have a step size that is small enough. So here we have 1 norm, here we have 2 norms, so it's not a mistake. And then this we have exponential convergence. So now it is the question, how can we get the theorem from the corollary? And the idea is to bound the step size by the value of the loss. And then we know the loss goes down geometrically. And by inductive argument that I already explained, we get this thing. So let us first get some technical thing out of the way. So there we will have some infinite sum of 1 minus mu eta t over 2. So this is equal to nothing special now. 1 minus square root 1 minus mu, and this is bound by 2 over mu. So this you can just by calculation, like to flip everything, isolate the square root, take squares on both sides, and so it isn't boring. But I just want to write it down because when we use it in a bit in the derivation, we don't want to waste time on this. Okay. So first step of the proof, L of W is C squared plus beta FW0 minus Y1 smooth. So why do we want this? Of course, we want to apply this result, and we know that 1 over eta is bounded by this thing. Is at least this thing. So we use here. So it's smoother with even bigger constant, then we are good. Okay, why is this true? Well, yesterday and in the seminar, we spoke about expression for quadratic, the Hessian for quadratic loss. Well, yeah, you need to do it once in your life, then you can remember, maybe remember this, because there are several places where it's needed. So it will be the derivative of f times the derivative of f. One is transposed, and of course I myself forget always which one. The first one is transposed. Plus, and then we have right from the next slide. Plus sum I smaller than m f w minus y times the Hessian y. So this is expression, and just like chain rule. So we have quadratic loss. So we can write it as a product of so the loss is a product of this with its transpose. So we will have the derivative going to both terms separately, and then 2 times. So then we will pick one side and keep it constant and pick 2 times the other side. So that's the idea. Okay, and now we can understand why LW is C squared plus this. Why we use C Lipschitz? C Lipschitz means that. What is yeah. But we want to mean C Lipschitz means that for every vector v, if we multiply df, so the norm of this thing is smaller than c times norm of v. So it's a constant of being c Lipschitz. So we take our 2 points that go very close to each other. And then the difference of the two functions by Taylor will be this value. So we have this thing. And so in the first term, we get c squared. Yes. Yeah, so when we compute v transpose HL of W times v, we sandwich this between v's, and then we get c squared here. And then for the second term, we again sandwich with two v's, but now it's even easier because we just multiply by the norm of all the terms. And then sum over this. So when we sum, so we get so the norm of this thing is bounded by the one norm. Okay, we take the one norm here and infinity norm here, in some sense. Okay, let's write everything because it's annoying. It's W. I forgot the index I again. So the I component of this one. Let's I minus yi. I. So we will break it apart here. We will break it. So we have a sum over I smaller than. So this will be bounded by the norm Vt. I of W minus yi times to the norm of H and I. That's Cauchy swap. Okay, yeah, it's yeah. I'll do it like this. Absolute values here because it's just a number. Okay, and this we can bound by normal v plus absolute. Yeah, just think.
No, it's a vector.
Yeah, it's a vector. Yeah, of course, yeah. It's a vector, but it's basically the length of the v by this constant. So here we have absolute value, and then when we sum, and here we can take two norm and norm of v and so on. Okay, this was before. Okay, so smooth is enough, and now. So the smooth, it means we can apply this. I already said it. If this step is okay. Now. Let us look to the size of update. So we want it to be geometrically small. E plus 1 minus the WT. And let us divide by the constants. I hope I guessed right. So we know that this is equal to eta times the gradient by definition of gradient descent. So we have 1 over c times gradient of W. Now we know that this is bounded by.
Why do we bound this? Why do
We need to. We say that if we stay in the circle,
okay.
then this is valid. And if this is always valid, we can apply this on each next step. Let me have a look. What can I do next? No, I think this is not great. Okay, and the gradient of L, I wrote it down somewhere. Okay, I almost lost, it was almost lost. Where is my gradient of L? Okay, then you have to do it in your head. So gradient of loss function, again, quadratic loss. So it says equal, so here is our loss. So we take derivative of 1 times this factor and multiply by this factor and lose the 1/2. And we know that the gradient of this factor is C Lipschitz because we add a constant. So when we take when we let the D operator work on this, we get a constant times this value. So what I'm using here is that gradient L of W is equal to D times F W minus Y times F W minus Y. We don't need. Yeah. So D transpose. But when we apply a vector to this thing, we know it's at most C times the vector. So the norm of this thing will be at most times C times this thing. So we have to look to this thing. So we know it's at most C times this. That's why I started with 1 over C. Start to remember things. And so here we have that this is bounded by F W minus Y. And this is very good news because this is equal to the square root of the loss. Actually 2 times the loss. And now we are done. So, because we know that the loss goes down exponentially fast. So now we can understand that W0 minus WT, this norm, we apply triangle inequality. This is sum of WT plus 1 minus WT. T goes from 0 to infinity. It's upper bound, right? So, okay, I should use a different letter, but it's not important. Okay, and now we know that this is bounded by this value, which goes down exponentially fast. So there is one more inequality. 1 minus mu T over 2 times square root of L 2L W0. Okay, it's a mess. I will write here next. So it is equal to square root 2L of W0 times sum over 1 minus mu to the power T over 2. T starts from 0 to plus infinity. Let me make some space. And now we apply our special sign here. And we conclude that this is smaller than 2 square root 2. So square root 2 LW0 divided by mu nu. Okay, and here so in this step I need to multiply by C eta. So here I also need to multiply by C eta. Eta will cancel. And what we get is 2C over mu times 2L0. So we have a little bit more. So I should say, let's say 4 here. Okay, and now we are finished. So now we are recursively done. At each update, we stay inside this ball. It means we can apply this result. And at the next update, we again stay in this ball because of the relation in the bottom. So that's the proof. And so here we have proven, actually something stronger satisfies this. And okay, let's call this S. And W T is in S. So that's a kind of inductive strong assumption, but that's the reason why we can apply this result. So now we have transformed our problem by, so we understand that this is bounded by a constant under the assumption of this theorem. And this theorem says that the gradient is large compared to the value of the loss. So now we still have to prove, okay, so there is a bunch of assumptions which are easy to satisfy in neural net. Like for C, we can C Lipschitz, we can satisfy for some C that doesn't depend on M. And this is because of our normalization constant. I've deleted the neural net. But okay, changing the weights. Okay, let us skip all this. The C Lipschitz is not so difficult. Beta smooth for one layer network. If you take a bunch of activations, okay, let us just go. It's easy to satisfy. Maybe I should add an exercise. Homework. Yeah. Okay. So yeah, but what is not so trivial is this condition here. So now our next task is, can we understand why with one hidden layer we have this condition? And that is where the neural tangent kernel is important. Okay, so I will tell you what is neural tangent kernel, and we can choose mu equal to the minimal eigenvalue of neural tangent kernel. And then our question will be, what is the minimal eigenvalue of neural tangent kernel? I will delete this. Well, actually, I can now delete everything. Just in case, let's remove the end of lecture. Definition. Well, there is tangent kernel, it's more general. So given a function f with m inputs to n values, the tangent kernel is d of f, w times d of f, w, and one of them is transposed. So we will sum over the derivatives, and that means we need to transpose the second. So let us write this as W. So this is n by n matrix, this symmetric n by n matrix. because here we have R n times F. So this is a kernel that's defined for pairs of points in the data set, just like we had kernels for SVM. And basically, a tangent kernel will reduce our regression problem to kernel regression, assuming it doesn't depend on W. And we already explained that the Hessian is very small, and this is the case. Okay, so let's do a few examples of what are tangent kernels. So imagine that F is a linear system, and W is equal to X times W. That's logical because X in machine learning, the rows are the vectors of the input. Okay, so then df of omega is equal to X, and the tangent kernel K doesn't depend on omega because this here we have a constant, is equal to X times X transpose. Okay, so now we want to prove the proposition I just deleted. So there were two conditions. Okay. So this is just an example. I will continue soon with this. I forgot to tell you something else, like why these tangent kernels are so important. Tangent kernel immediately gives us new PL condition by minimal eigenvalue. So there is a nice lemma. Let me put it below here. So let us look to the squared norm of the gradient of quadratic loss. So that is L of omega transpose times gradient of L of omega. So how can we write this? No, first I should say the lemma, not the proof, of course. Lemma 1/2 L is without 1/2 is bigger than lambda min of K of omega times L. So we choose the minimal eigenvalue of tangent kernel as the value of mu, and we hope that it's bigger than we hope it's strictly bigger than 0, and then we get this exponential convergence. Okay, so let's prove the lemma. And it's just writing. So remember what is gradient of L? It is equal to V of F transpose times F minus Y. So this norm squared will be gradient of L transpose times gradient of L. So it is equal to F minus Y transpose times df times df transpose times F minus Y. Okay, and now this finishes the proof because this thing is tangent kernel. So here, so when we take minimal eigenvalue of tangent kernel, this is bigger than lambda min of K times norm of F minus Y. And I forgot to 1/2 here. So now it's nicely tied. Okay. So now we understand why this helps us. now we also understand why we care about the minimum eigenvalue of tangent kernel. We also need to know, so imagine that we want to solve a linear set using a linear system of equalities, over parameterized system of equalities using gradient descent. So then we want to prove, use the previous proposition that I just deleted. So we don't need this advanced thing because if eigenvalue, min eigenvalue is strictly positive, so its matrix is positive definite. So okay, so let me say again. So we want to solve a system of equalities. So xw equals y. So our system is over parameterized and we want to do it fast using gradient descent. Then we can, we want to choose, we need that our function f is a beta smooth. And in the previous thing, we have 1 over eta smooth. So in the previous proposition that I just deleted. Okay, what means 1 over eta smooth? It means that Hessian is at most 1 over eta. Hessian of loss function is at most 1 over. So here we have the loss function has to be 1 over eta smooth. Okay, so what is the Hessian of the loss function? So for this, remember about the formula that I gave you. So the Hessian of the loss function, quadratic loss, it's a constant when we have a linear system. So our loss function L over W is equal to this and so on L. So the Hessian will be a constant and it will be given by d of f. So f is xw minus y. So here is f. And recall what I said about Hessian for loss function. It is equal to d of f times d of f. Oh my god. Now the transpose is here. And so in our case, d of f is simply the matrix x. So we have x transpose times x. And now notice the difference between the Hessian and the tangent kernel. So the difference between this and this. So here we have x transpose, here we have x transpose and x. And here, now we are interested to recognize smoothness of L. And we are interested in the largest eigenvalue of x transpose x. And so this largest eigenvalue is the same eigenvalue as so lambda max of HL is the same as lambda max of neural tangent kernel. Because of this relation, it's an exercise in linear algebra. So the K and HL have the same non-zero matrix eigenvalues. So and this leads us to an interesting observation on convergence of gradient descent when you solve linear systems, linear inequalities. So we have eta is 1 divided by the largest eigenvalue of neural tangent kernel. U is equal to the smallest eigenvalue. So gradient descent on this loss function with eta equal to 1 divided by step size equal to divided by lambda max of K gives speed 1 minus lambda min of K divided by lambda max of K. So the exponential factor that we gain here, well, we're applying the simple proposition, is 1 minus lambda min divided by lambda max. Then there is this important number that's called condition number. It's usually denoted by kappa. It is the inverse of this value. And they say if the condition number is equal to lambda max of k, so the condition number of k is equal to, well, the condition number of x, sorry, is equal to lambda max divided by lambda min. Well, actually, I'm not sure whether it's condition number of k or x. I thought x is defined by this thing. And it's well known, if this condition number is large, then operations on this matrix X are difficult to implement. They're slow to implement. And so here we see that also gradient descent, and this is a symptom of this. Gradient descent converges slowly if condition number is large. Well, this is, so there is some nice connection. Okay, but we are not finished. We need to prove why gradient descent, why lambda min, why this kernel has minimal eigenvalue that's positive for a neural net with one hidden layer. And so it's slightly, I didn't prepare it, but it's kind of easy to understand. Because let us look to how it's defined. So this is an n by m matrix. So here we have a huge sum here inside. And here, the sum, what are the terms inside the sum? So let us look at the component, K alpha. Or maybe I should just write down for our one-layered neural network. It will be much more clear. So let us go back to the network. So what I will say is that when we take a random initialization point W here, we will have huge sums, and all these sums are random variables that are identically distributed. In our network, in our neural net, F is the output neuron, which take the sum of over many neurons that are somehow stochastically initialized, but have the same output distribution. And we will normalize by 1, and the output is normalized by 1 over square root m. So when we take 2, we will have an average. When we calculate this, we have an average over many identically and independently distributed variables. So we will have something that converges extremely fast to a fixed value. And so when we, our task is to write down this value and then observe that it gives a positively finite kernel. So note again that n is some small value, m is huge. So we know that each element goes to a fixed value. We just need to see that when we take linear combination in certain ways, it is bounded away from 0. It's not so, even for one hidden layer, it's not completely obvious. I mean, I can write it down and it's kind of plausible for radioactivation. This expression is quite easy. But I didn't try to foolproof yet. I hope to do it tomorrow, but it will not be for exam. I will just write it down now and it should be kind of plausible. So let us remember what is F. Let us say that F alpha. So alpha is an index from the training point. So F alpha of W is equal to 1 over square root m, sum of okay, let's use real. So we will have then we need all the vectors here, W1 to Wm. So here we will have Wi times x alpha. Not an indicator function, but the maximum of this and 0. And that's it. And I goes from 1 to n. So that's our function. So now what is tangent kernel? So let us look to component KAP. So we need to have a sum over all indices. A sum over all parameters. So we take the derivative to all parameters. And so let us remember what is partial derivative. It will be indicator function WA times X alpha is at least 0 times we need change here. And at least something is right. And so here we have X alpha, the J component of X alpha. So here is the partial derivative to Wij. And we have to do the same thing for this thing here. So what I'm doing now, K alpha beta of W is equal to gradient F of W transpose times gradient of FW. So this one I'm calculating. I calculated the first gradient. But now we have to double indices to go over this vector. And then we do the same thing for the gradient 2b. And beta x beta. Okay. So when we calculate the sum, we can simplify a little bit. Because when we, so the brackets do not depend on J, so here we get just the dot product. So we have a sum over all I of Wi times X alpha, Wi times X beta, and then the dot product of X alpha times X beta. And this is, oh, sorry, and I lost the 2 times square root 1 over n. So here we have 1 over square root m. Here we have 1 over square root m. So here becomes in the front 1 over m. And so here we see that this is just empirical. So when we take wi's, all these vectors randomly, we just get an average estimate of this factor. And this can be evaluated exactly. So in case of real, we can get this exactly. Because look what is here, an indicator function. I didn't write it correctly. This is bigger than 0, and this should be bigger than 0. So look, we have 2 vectors, X alpha and X beta, and then we check, we take a W. So for each neuron, we take a random W, and we check whether they are both in the half space. And we check whether X alpha and X beta are both in the positive half space. So this is like we only need that Wi is like symmetric under rotations. And if this is the case, we get this nice expression. It is it will be pi minus arc cosinus of X alpha times X beta divided by the norm X alpha X beta. So this will be the expected value of K alpha beta. So over initialization of W. Okay, and so now people have checked that this is indeed a positive definite matrix. Right? So it sounds very plausible. And also from measured concentration, we know that M is large, that this random variable, that its average will be close to its expected value. By who have they bound? And so this explains why this K alpha beta is has a minimum eigenvalue that is large. Okay, so where are we now? Oh, yeah, it's finished. Okay, it's time, just 1 minute. So let me explain. So where are we now? We have proven that the minimum eigenvalue, well, we didn't prove it in details, but okay, we can understand what is K alpha beta for real functions. For general activation, we don't have expression, but we can prove its minimal eigenvalue is bounded away from zero. But this is only in the initialization. We need it in a small ball. But note that tangent kernel is built from gradients. We know the gradients are stable. By the same technique, just a little more equations, we can prove that the min eigenvalue of just any eigenvalue of tangent kernel is stable when we stay inside such a ball. And this finishes the whole story of the miracle why neural tangent kernel and gradient is stable for training. Okay, so now one last remark. I said that there is experimental observation. Maybe it's a bit weak, it's not clear to me at the moment, that fast convergence lead to smaller test error. So there are ways to check this empirically by adding noise on the labels. So why does this happen? For this, you can write down, to understand this, you can actually write down an analytical solution of continuous gradient descent. Continuous gradient descent is that if you take the limit of eta, the step size, to 0, and look to which point you arrive. And there exists analytical solution of this equality, and I will just write down this analytical solution. The derivation is really interesting, so I will try to put it in the notes, but you don't need to know about this. So for example, so let us say that so we have so what we will do is we will have a parameter t that's now continuous. So it takes a gradient descent in very small steps. And so we have fwt as a function of, we view it as a function of time. And we know that the time derivative, it's a dot, it just, okay, that's the consist, more familiar notation. One can prove that this is equal to the negative of tangent kernel times f of wt. And so this differential equation, but no, there are vectors here. This is n by n matrix, and this has a solution that says that fwt, so y minus fwt, fw0 is equal to e to the power minus k w. I don't remember, but there is an exponential function, and the conclusion is that the value f converges to y if tangent kernel is of full rank. So this will converge to 0. So here is a t. I forgot. So okay, I forgot what is in front and at the back of the exponent, but it doesn't matter. The conclusion is that this goes to 0 if all eigenvalues are positive. And now we can understand what happens. If convergence happens fast, only in this exponent, only the large eigenvalues are dominant. And it means that the solution y only contains Sorry. Let me write something that makes sense. WT minus F W0 is equal to or something like this. I hope I'm right. Okay, so what I'm saying is that if this converges fast, it means that just the large eigenvalues only have time to contribute to the exponent. And that means the small eigenvalues have zero influence. And that means that the span, which I wrote in the beginning of the lecture here, not all eigenvectors from the column space are used, only the ones, only eigenvectors with large eigenvalue are used when gradient descent converges work. Okay, but this is philosophical. Sorry, I missed it. I forgot the details. So this is all for the course. Tomorrow I will put colloquium questions online tomorrow morning, but they are the same. If you want to learn in the evening, there may be one or two.
Will be next Tuesday or the Tuesday?
You can choose.
Okay.
So just come to the lecture.